So we continue with the second half of the second lecture. Okay.
Okay. Thank you. Welcome back. All right. So we finished with this formal definition of learning. Now I want to talk about this notion of complexity that allows us to make some descriptions of learnability for cases where the hypothesis class is not finite. And the growth function and the VC dimension. Part of the idea here is based on this observation that if you have a finite set of data points, then the number of functions that you can instantiate on that finite set is finite, at least for binary classification. And so somehow we want to make we want to exploit the observation that there are only so many ways in which you can do binary classification on a finite set of points, no matter how many hypotheses you have. And so this ends up meaning that a lot of these events that we were talking about, where we use this union bound, actually overlap. And this union bound, we can do it more smartly, ultimately, geometrically. So let's consider a finite subset S of the input space X. And then for a function class H, the restriction to the set S, we can denote it by H restricted to S. That's going to be our hypothesis set restricted to that set. The set could be a training data. And then we can view the cardinality of H restricted to S as a measure of the complexity of this function class H with respect to this set S. And we can compare it to 2 to the power S, which would be the total number of ways in which we can do binary classification on a set of cardinality S, or absolute number S. All right, so then we're going to define here the growth function. It's going to tell us essentially how big is that. So if we set our set S, so we consider any subset of the input space. Let's say it has cardinality M, and then we look at our hypothesis class restricted to any such set S of cardinality M. What is the maximum size or the maximum cardinality that we could obtain? So it's the maximum number of hypothesis functions restricted to input set of cardinality M. That's going to be just some number, and that number as a function of M is called the growth function for this particular function class H. So how quickly does the function class grow as we increase the size of the sample in the worst case? So we're taking the maximum here that will allow some flexibility with the arguments later. Observation, this thing is bounded from above by 2 to the power M, because when we're given n data points, we can say plus minus on each of them, and there are 2 to the power n different options. Also, if H is a finite set, then certainly this growth function will be bounded above by the cardinality of H, if it is finite. So it's going to be bounded by either 2 to the power n or just the cardinality of H. And so a little bit more terminology, we call a dichotomy one of the functions from the subset S to 0, 1 in H restricted to S. So any of those restrictions of hypothesis function to our input data subset S is a dichotomy. It's an assignment of class labels to a finite collection of input data points. Okay, definition.
What was the target in general? It's not 0, 1, but target could be.
In general, the output value could be something, could be a real number, could be a vector, and we're looking now at the particular case where it is 0 or 1. Yeah. All right, so then if we just try to make this a little bit more concrete, we can look at the simple perceptron, just coming back to this. These are model of functions here from Rn to 0, 1. And what we're doing is we compute this affine function of x, and then we apply this sigma, which is just the sign. And what we're going to do is produce value 1 if whatever was the argument was non-negative, and value 0 otherwise. This is kind of the linear classifier that we had before. We apply a linear function. If the value is non-negative, then we say this is +1, and otherwise this is +0. How many dichotomies on 2 points that are sitting in R are there for the simple perceptron?
It is 4, I'm just kidding.
4.
It's every, let's see. Your input is 2 points, right?
Yeah.
And output is 2 points.
Yeah. No, output is 0, 1.
0, 1.
Yeah, 4 sounds about right. Okay. So okay, 2 points in R, so we can have the linear function. So it's going to be like this, or we can put the threshold over there, or afterwards, or we can revert it. So we can get actually 4 different dichotomies. Both points are classified as 0, both are classified as 1, 0, 1, 1, 0. More generally, the growth function for the simple perceptron turns out to look like this. So if H is the set of functions computable by the simple perceptron with inputs in Rn, then this growth function takes this particular value 2 times this sum, n minus 1 choose k, for k running from 0 to n. N is the dimension of the input data, and n is the number of sample points. All right? So this formula looks familiar. Yes? Where have you seen the formula?
It looks like something from moment generating functions. I believe I saw this.
Generating functions.
Yeah.
Okay. Yeah. All right. So this formula looks familiar. At least one of the places that this formula arises, and it's a very nice one, is this so-called cutting cake problem, where, and I'm going to try to explain in a moment how that comes about. So we're getting a cake, and we're going to ask to cut the cake a certain number of times. We're going to be asking to cut it m times. And the question is, how many pieces can you get by doing that? So that cake in n plus 1 dimensions, we're going to cut it m times. How many pieces can we possibly get? And I'm going to explain why this formula appears here. Right, so the idea is going to be that we're going to divide the set of parameters of the function class H of the simple perceptron into different pieces. Those are the pieces of the cake that represent the same dichotomy over a particular set of input points S. So as I was saying, we will have an infinite number of different hypotheses, but when we restrict them to a finite data set, they have potentially, many of them have the same, represent the same dichotomy, and those are the different portions of the parameter space, and there are infinitely many of them, even though there are infinitely many different linear classifications or linear classifiers. In the eyes of the finite data set, they are all the same, or many of them are the same. Okay, so first, this is the observation. The number of dichotomies can be expressed as follows. So for a set of input points, x1 to xm, we let this p1 to pm be hyperplanes, and they're going to be defined like this. So we're going to take this affine function, so wx minus b. This is the affine function that we compute in the simple perceptron, and we equate this to 0. And this is going to be for the input data point xi. and the set of values of W and B, set of parameters, such that for the input data point xi, this is 0. You can think of this as what are the parameters of the simple perceptron so that it is undecided about the class of the data point xi. So this happens to be a hyperplane in this case because if we equate the output of our function at the input point xi to 0, or to where we're undecided between the classes, then that solution set is a hyperplane. It's a solution to a linear equation. And the statement here is that the number of dichotomies, so this one, the cardinality of H restricted S, is equal to what I'm writing down here is we take the union of all these hyperplanes and we remove that from R n plus 1. R n plus 1 is the space of parameters, so we call W is in Rn and B is in R. So this is the intercept and W are the weights that we're using here. So in that parameter space, we remove those hyperplanes and we are then left with some regions. And so the number of regions that we're left with, that is going to be supposed to be the number of dichotomies. So every one of those regions is all the parameters where you are representing the same dichotomy. That should make sense because if you think about a particular data point and there are some parameters where you're undecided about the value, so if you leave that region of parameters, you're going to start classifying that data point either as positive or as negative. Unless you cross another one of those indecision surfaces, you're going to still continue to classify all the data points in the same way. So therefore, it's a cutting cake problem. So you imagine that these hyperplanes are the slices, the cuts that we're doing, and we're cutting multiple times, and the different pieces that remain, those regions correspond to the different dichotomies. Okay, so and now that we have this, how difficult is it actually to convince ourselves about the number of pieces that we can get when cutting cake? Okay, so this is just an explanation of what I just mentioned, that the number of regions that we're left with there is the number of dichotomies. It's an illustration. So this is the case for 2 points in R, and so the 4 dichotomies. Yeah, so we get exactly 4, and one way to see that in R is that the parameter space is R2, and we're going to get, for every one of the data points, we get a hyperplane. So we get 2 hyperplanes, and they cut R2 in 4 pieces, and here we have maybe one piece where both data points are classified as negative, one portion over here where both of them are classified as positive, and so on. And there are 4 of them. So if we were to have 3 data points in R, how many dichotomies do we get? Okay, somebody says 7. So it should be 7?
2 to the power.
2 to the power 3, 8. Okay, but for the simple perceptron. Okay. We can look at this formula, and this formula is, for n equals, we say 3, and n is equals 1. So we're summing 2 choose 0 and 2 choose 1.
2 choose 0 is 1, 2 choose 1 is 2.
So times 2 is 6. Okay, so 6. So in this picture, of course, if we were to put 3 hyperplanes, here we have 2. If you put 3 hyperplanes, we essentially maybe get another one over here. We get 1, 2, 3, 4, 5, 6. Right. So, I guess part of the reason you said 7 is because what happens if you put here a hyperplane that doesn't go through the origin? So then you would get an additional 1. Yeah, so but in this picture, like if we go back and look at what are these indecision surfaces, so these guys, if we think of them as being in Rn+1, then these are homogeneous equations. They don't have an intercept. So therefore, these hyperplanes are actually going through the origin. All right, so now we need to count the number of regions. As I was saying, how do we actually show that the number of regions is equal to this formula? And so it's a statement now about some sort of geometric combinatorics. So regions of a central arrangement in general position. So if we take the data points to be in general position, then this hyperplane will be in general position. And how many regions do we get? It's a problem that people have studied for many years. And this is the value. And as a matter of fact, it's not terribly difficult to prove this. And so I'm going to try to give you a sketch of a proof for the statement. All right, here's how it goes. So we proceed by induction, and this is maybe sometimes called a sweep hyperplane method. And the induction is quite beautiful. So we're going to fix D, the dimension, and we consider an arrangement of M hyperplanes. We have M hyperplanes in RD. Let's call them P1 to Pm. And let's now imagine that we're going to add one more hyperplane, Pm+1. And so we can ask how many new regions are emerging by us having adding either Pm+1. And this is going to be the number of regions that we had before, plus, added to that, the number of regions that we observed in the hyperplane Pm+1 as produced by the previous hyperplanes. Okay. That makes sense? Okay. Picture maybe. So I'm going to do this as hyperplanes that are not going through the origin, but just for simplicity. So, maybe like so. These are the P1 and P2, and now we're going to add one more hyperplane, maybe this one here. This is Pm+1. And so the number of regions that we had before was 4, and we added this guy here, and so we have 3 new regions. The 3 new regions correspond, if you think just of Pm+1 by itself, so it actually is sliced by the previous 2 guys, like so, into 3 pieces. So we're adding the 4 that we had before, plus we look at the arrangement of hyperplanes over here, which has 3 ones, and those are the ones that we're adding here. So that will allow us to do an induction. So essentially the induction goes like this. The node now by R, M, and D is just how many regions do we have by a certain number of hyperplanes in a certain dimension. So we have R of M+1 in D dimensions is equal to R of MD, the previous number of regions, plus R with M hyperplanes for 1 dimension less, because we're now evaluating this over the hyperplane itself, which has 1 dimension less, D minus 1. So the first one is the previous guy, and the second term is this guy. We want to use this for our induction. Now, this hypothesis, this formula, 2 sum of n-1 choose k, we can convince ourselves that this holds when n is equal 1 or when d is equal any d. And that's true because if n is equal to 1, that means we have just one hyperplane. This always splits the space into 2 pieces. And that's the value that we get from the formula. And it also holds true when d is equal to 1 and any number of hyperplanes, because they are central hyperplanes, and so we're always splitting just the real line, which is something at the origin. We always get 2 pieces. And that means that if we look at this table, this is a table where in the case that we have verified, M changing across rows and D changing across columns. So we have verified all the cases. So, and now we need to kind of combine two cases together to obtain the next case over here. If we can do that, we can end up filling up the table.
It's induction on M, right? On the number of
M and D, yeah.
induction on M and D, or on M. M equal 1, 2, 3.
On both.
So I haven't seen that too.
I'm going to tell you in just a moment. So yeah, so like let's say we have verified this row, and now based on this we can move to the next value of M. Oh yeah, for all these examples, for M. Yeah. Induction on M, yes. Yeah, we're going to do induction on M. All right, so induction on M. So if we have verified the case for MD and MD minus 1, we now want to prove that it holds for M plus 1 MD. And so we just put here this recursion that we had and the induction hypothesis inserted there, and just some manipulations actually end up giving us the result. So now it's just manipulation. Yes, please.
Does the formula, does it work for if you're just on the line, if you're just thinking about so it's like partitions, like successive partitions of the real line? Then can you still do this? Like, can you just do this in R1?
This holds for any dimension, not just for R1.
Yeah.
Or were you suggesting to use something different than a hyperplane?
A hyperplane in R1 is just like another split. You're just choosing their split, and then you have two splits here, and you have another split here, right? So it seems like, does the formula work if you're just thinking about like breaks in the real line? Maybe I'm misstating the thing I'm thinking about.
Okay, this will work not only for lines, but also for hyperplanes in any dimension. And
were you asking if it holds even for dimension 1?
Yeah, and that's even for dimension.
oh yeah, in particular it holds for dimension 1. Yeah. But in the case of dimension 1, as I explained, that is part of kind of our initial statement here. So dimension 1 is kind of it's very easy to verify that because all our cuts, all our hyperplanes are passing through the origin. So in dimension 1, we are just cutting at 0.
Yeah.
So you're saying if we were to be doing something like this for hyperplane arrangements that are not going through 0,
Yes.
you could still do something similar. Yes, that's correct. Okay, then to conclude the theorem now, what we need to do is to make sure that we're dealing actually with the worst case, and so so hyperplanes in general position produce the worst case. That's not too difficult to see that, and they actually produce the maximum number of regions. So if you wiggle some hyperplanes a little bit, none of the regions are going to disappear, but it could be that you have a degenerate case where hyperplanes are on top of each other. If you wiggle them a little bit, then you can have new regions emerging, and that will give you the maximum number of regions. Right. Then, so we have here that the growth function of the simple perceptron is given in this way. Is the number of regions defined by a central arrangement of M hyperplanes in general position in n plus 1 dimensions. It's kind of nice. It's a maybe useful remark here to make at this point for general not central arrangements. There is a similar statement that can be made. This goes back to the question that was asked here. So if you're not cutting just at 0, in that case the number of regions looks like this. So we have replaced here a little bit, instead of having a 2 and an n minus 1, we have this kind of expression. And it is also possible to say something about the number of bounded regions. So if the hyperplanes are going through 0, all the regions are unbounded and they are just cones. But if they are not going through 0, you can end up having something like this. Let's say a bounded piece here, and one can say something about the number of bounded pieces, like so. This is for hyperplanes in general position. there are actually also very beautiful counting formulas for arrangements that are not in general position. This goes back to Zaslansky, very celebrated work. All right, this is just a remark that if you have a formula for hyperplanes that are not central, you can come back and obtain a result, or the result for the central hyperplane arrangement. But I'm not going to go too much into the details here. All right, so then let's come to this notion of shattering. And shattering is when we have a function class and we have a set S of endpoints in the input space. Then if H can compute all the dichotomies of S, then we say that H shatters S. So that means that the restriction of H to S has cardinality 2 to the m. So that H shatters S. First dimension, the first definition. The second one, the VC dimension, the Vatnik-Chervonenkis dimension. So these are the two guys that develop a lot of the framework of statistical learning, and this concept is named after them. Is defined like this. So the VC dimension of the hypothesis class is the maximum m, the maximum size of a data set, so that the growth function takes value 2 to the n. So what is the largest size of a data set that you can shatter with this hypothesis class? And it generally makes sense to think about this as a complexity measure. So how many data points at most can you classify whichever way with your hypothesis class?
Is it like a topological dimension or something? What dimension is equal to 1?
It's a name. There is going to be, I promise. So, this is kind of a combinatorial quantity, but yeah, you may be interested in relating this somehow to some degrees of freedom to some extent, and therefore calling it a dimension. And yes, it's a combinatorial quantity, but it turns out to have a lot of connections to geometric notions, maybe as is already indicated by the picture that I showed with this cutting cake problem. And as it turns out, this simple combinatorial quantity actually will tell us a lot about the complexity of learning. And so we're going to discuss that also in a moment. Yeah, links to topology as well. There's really a lot of interesting connections that we could draw to this quantity. All right, so we will see that the behavior of the growth function is tightly connected to the VC dimension. It's tightly constrained by it. So in a sense, so we say the growth function is, what is the number of dichotomies that you can express on a data set of a particular cardinality, and the VC dimension is telling you what is the largest size of the data set for which that number is 2 to the power n. And here as an example, one thing that happens is that, so the growth function of the simple perceptron was this formula. We just convinced ourselves of that. And this formula actually takes value 2 to the power m if and only if n is larger than or equal to n minus 1. So just by looking at this, so we know that this sum evaluates to 2 to the power n if m minus 1 is larger than or equal to n. And we have the 2 in here, so we want this to evaluate to the power m minus 1 times 2 is to the power n. And otherwise, it's going to be less than that. And so the VC dimension of the simple perceptron is n plus 1. But now, what we want to say is that this fact actually will tell us a lot about the growth function in general. So if we know that if dimension is this number, this is going to constrain the way in which the growth function is growing. Okay, so this is kind of recapping. So the simple perceptron with n real valued inputs can structure a set S if and only if the set consists of finally independent points. And in turn, so since there are at most n plus 1 linearly independent points in Rn, the VC dimension is going to be n plus 1. So we, I guess so far we actually saw a proof of the growth function for the simple perceptron, but now we can say, maybe we can try to see this more explicitly and say something about this dimension itself. So we quick argument for this. So a simple perceptron is a set of functions that assign value 1 to the positive side of some hyperplane. And let's think about the case when the data points are finally independent. And what we need to show is that whatever dichotomy we place on that data set, we can represent it with a simple perceptron. So we're going to construct the weights that represent this particular function, this particular dichotomy. So let's call that F. Oops. And let's denote the input points out of the set S, which are labeled positively as S plus. And so since the data points are finally independent, that means that if we append a 1 to each of the data points, these kind of augmented vectors are linearly independent. That's what it means. And so since those vectors are linearly independent, that means that so we can find other vectors v1 to vm that multiply with each of those augmented points to give 1 if and only if the indices agree. So Vj times Xj is 1 and Vj times Xi is 0. Different from right? So in a way, so we can also arrange the data like a matrix like this and say, okay, this matrix is going to have full column rank and none of the columns can be represented as a linear combination of the others. That's the geometric picture. And then now we can construct the weights as follows. So we take actually the V to be the sum of the Vj's with J in the positive class for the target dichotomy that we want to represent. And if we do this, then we're going to have this property. So we multiply this whole thing with Xi. We're going to get 0 if Xi is in S minus, and we're going to get 1 if Xi is in S plus. That's because of the way that these Vj's work. So the Vj, recall, it will produce value 1 only if you multiply with Xj and value 0 otherwise. So we don't have here any of all of the other x's that are not in S plus are not appearing in this sum. So then we're going to multiply to 0, and the otherwise there's going to be just one of the x's will multiply to 1. Right? So therefore, this perception will compute because now you see that we evaluate the sign of this. This will classify the points in S plus positively, and the points we're going to classify negatively. Which is exactly what we wanted. Now, what about the other direction? The other direction, now we want to construct or come up with some labels, some dichotomy, and show that it cannot be represented by the simple perceptron. And how to do that? Now, of course, what we want to do is use the fact that the data points are not affine independent and try to construct some kind of contradiction. So let's suppose that the set S is not affine independent, and that means that we can represent one of the columns as a linear combination of the other ones. And let's just do that construction. So let's say that this particular column can be represented as this linear combination of some other columns. And the weights, let's call them alpha i's. We're going to define the target dichotomy as assigning value psi of alpha I to xi. That's just some construction, and value 0 to x1. And now we're going to show that this is going to be a contradiction. So if the perceptron can represent the dichotomy f, then something has to be true. There must be some vector v so that you get the correct sign. And you know, this will be true for all i's, but if you plug this into the definition of this, you know, of this dichotomy, of this target dichotomy that we had, you're going to end up getting a contradiction. So you know, this means that you cannot represent that dichotomy with the simple perception. So long as the data points are not finally independent. Okay, so then, you know, this shows that, you know, a set of data points can be shattered by the simple perception if and only if the data points are affine independent. And the maximum number of affine independent vectors in our n is n plus 1, and so we're finished. So the DC dimension is actually n plus 1. Comments, questions, concerns? Okay. What is our time? Okay. Then maybe this is an interesting generalization here that I want to mention. The theorem that I showed you before, it can be extended in the following way, which is quite meaningful, I think. So we're going to think of the hypothesis set now as being not the signs of linear functions, but the signs of functions that are in some linear space, in some vector space of functions. So we're going to take sign of f plus g, where f is any element in a vector space of real valued functions, and g is some fixed real valued function. Then the VC dimension of this set H is given by the dimension of that vector space. And the simple perceptron would be a special case of this, where this vector space is just the span of all the coordinate functions plus the constant function equal 1, and g is the 0 function. So of course, any linear function can be written as a linear combination of some elementary functions. And the set of elementary functions, you can take any linear combinations of those, and those are still giving us linear functions. So that's a special case of this theorem. This theorem is more general. And it is quite nice because it tells us, you know, that the dimension is in fact the dimension of this vector space. All right, so here's a couple of examples. So for the classification with a linear classifier, we always get hyperplanes. That's the picture to the left. And to the right, I'm showing you some examples of classification with functions from a vector space, which is the vector space here of polynomials. So we do basically classification by taking the sign of a polynomial here of degree 2. So it could look like this, or like this, or like that. And you can tell that in the left-hand side, you know, we're always separating the data with a hyperplane, and the right-hand side, we're separating the data maybe with a parabola or with some other ellipse or circle, things like that. And somehow the statement we're making is the dimension of the space of quadratic functions that's going to be informing us about what is the largest cardinality of a data set that we can classify whichever way with that particular model. Or in turn, you know, we would see how many data points do we need actually to obtain the best possible parabola to classify data. All right, so the proof for this, this is now actually a simplification, in fact, of the proof that I gave you before, and the idea is going to be that we take a basis of this vector space of functions, and we evaluate this basis over some data set. So we collect this into columns, much as we did before for the simple perceptron. So these are the columns here. Every one of these basis functions evaluated over the different data points. And so since our hypotheses are linear combinations of those basis functions, like we have some particular hypothesis from our set, this is going to be a linear combination. It's going to be a multiplication of that matrix with some vector coefficients, and we had the fixed function g as well, and we add that here. So we have this entire expression here. And if we want to represent a dichotomy over this data set, that's going to mean that this entire thing is going to correspond to, is going to have some signature. And yeah, so now we can think about this geometrically. What does it mean that we have a particular signature? It means that we have identified here some weights W that we can plug in there and we get some sign. So we can look at what is the space of all the possible vectors that we can get as we modify the parameter W. There's going to be some kind of plane, because it's a linear system. And this plane, we're asking if it's going to be able to intersect some orthant. Some orthant of Rm, right? Intersecting an orthant of Rm means that we are assigning some particular dichotomy. Geometrically, we can tell, are we going to be able to shatter a set of some cardinality m? And that would mean that we have to intersect all orthants of Rm. And it is maybe intuitively clear, but it can also be shown that you can only intersect of all orthants of Rm if your linear space has in fact dimension m. So if and only if d is equal to m, you can intersect all orthants and therefore shatter that particular data set, and hence the maximum number of points that you can shatter is d, which is the dimension of this vector space of functions. That's it. So it's pretty nice. All right, so now we still need to connect the least dimension to a growth function.